Weather and climate models are powerful tools for the physical representation of the processes in the atmosphere, surface, subsurface, and in the ocean. A large ratio of the data provided by model simulations cannot be directly measured. However, we know that model simulation data show uncertainty due to model structure, parameter errors, model forcing errors, and initial value errors. In fact, mismatches always occur between the model simulation data and measured observations. Therefore, model simulation data need to be merged with observations to improve the accuracy of model-based data. There are some key challenges in merging model-based data with observations. First, observations are not complete, meaning that they are not accessible at all required time or locations. Secondly, models may be used to make predictions about the future. Observations, on the other hand, are only available in present or as historical data. Therefore, we can only rely on historical relationships between them. The goal of merging model-based data with observations is to combine the advantages of both, to arrive at an improved simulation data. There are many available approaches for merging. Here, we briefly talk about the statistical methods, data assimilation, and data-driven methods. Bias correction is a popular statistical method for merging. Bias correction assumes that model observation mismatches represent the model bias. The historical observed data are regarded as the ground truth, and a certain statistical attribute of the model estimates are shifted or rescaled into the same statistical attribute of the observations to correct the bias. A popular example of bias correction method is CDF matching. CDF matching is a method to remove the systematic errors by matching cumulative distribution function of model data and observations. Data assimilation is another merging method used for decades in climate models. The basic data assimilation framework is based on this equation. The model analysis or the best estimate is given according to the model estimate, the error weight, and the model observation mismatches. The error weight in this equation accounts for the uncertainties in model estimate and observations and defines how much the model analysis is inclined to the model estimate or observations based on their uncertainties. The calculation of this error weight is dependent on the statistical assumptions, such as Gaussian-like error distribution. In recent years, data-driven methods such as machine learning and deep learning have also been used in merging. A classical approach of using deep learning in merging is direct mapping of observations from the model-based data. In this approach, the weights in the deep learning network are trained such that they make predictions of the observations given the model-based data. Another approach is training the deep learning network on the mismatches between the model-based data and the observations. This way, the deep learning network may predict the mismatches given the model-based data to the network. The biggest advantage of using data-driven methods, such as deep learning, is their independence from statistical assumptions and limitations that are present in statistical methods and data assimilation. However, the limitation of deep learning approaches is that it may be impossible or very challenging to interpret the relationships between the inputs and the outputs.